Okay, we're going to get started here. If Before we get started, though, if I could ask anyone who's listening in to mute your screen, just so we're not picking up the background noise at your location, and it's not distracting the other listeners. Good morning. My name is Blaine French with Rockwood Retaining Walls, and I want to thank you for taking the time to join us this morning. A couple of weeks ago, we started a program called Webinar Wednesday with our sister company, Rochester Concrete Products here. And largely due to the request of getting additional product training and the shelter-in-place requirements that were put in place because of COVID-19. But it's really been very well received. And we've been recording each webinar and posting them to the Rochester Concrete website. So people can view them at a more convenient time that might work out for them. And what we've noticed is even 2 to 3 weeks after we have posted these to the website, we've had significant traffic for people going through and looking at the webinars. So today's session is going to be recorded as well, and it will be posted to the Rockwood site probably here by the end of the week. The title of the presentation is Segmental Retaining Wall Design and Best Practices. And the content that we're going to cover are Rockwood products, and not all of them for sure, but kind of the new and the old, and go through some of those features and benefits. And if you're giving a presentation to an engineer, architect, some important features, benefits that you might want to point out, or potentially new stuff that if your company hasn't considered getting into certain lines, maybe possibly adding those. We're going to go through some segmental retaining wall terminology, design considerations. So it's not heavy engineering, but really understanding what are the important aspects of things that you might see on a site that relate and could affect the overall design or structure of a retaining wall. Agency requirements and permitting, and then also best practices for construction and why these best practices are important, which is maybe a little bit of a teaser that we might have some when walls go wrong or some failure slides to kind of finish up the presentation. Look at some applications. So Rockwood offers a wide variety of products for different applications, and we have a lot of different tools for your toolbox of selling segmental retaining walls. Rockwood products are really suitable for a wide variety, from backyards to residential developments, commercial developments, to highway and transportation work, as well as institutional use at schools, hospitals, and even industrial sites. So we really have a product that will fit virtually every application and be suitable, and many times the best choice for an owner or developer when it comes to solving their grade separation needs. What I want to start off with is kind of the workhorse, the Classic 8. And it really has been kind of the main workhorse for commercial and larger residential projects for the better part of 20 years. As you can see, it is available in both beveled face and straight face. They're 8 by 18 in size, so each unit covers a full square foot. You can't see it here, the underside of the block where the alignment bar is. That alignment bar is placed down over the top of 2 units below and pulled securely forward, and that gives you your automatic setback or batter. The standard batter for the Rockwood Classic 8 is 8 degree, which is basically 1 inch per course, but it can also be manufactured as a near vertical by putting a spacer in the mold to create more of a near vertical appearance, which that could be important if you're on a commercial site that has tie-ins to buildings and things like that, where you need to be more vertical at your tie-ins or taller walls with radiuses. Those different site conditions may be more conducive to have a more vertical unit. The Classic 8, or the Classic 6 is just like it says, a smaller version of it. It's only 6 inches in height, but it's still 18 inches wide. And it really has many of the same product features and benefits as the Classic 8. This 6-inch profile, a lot of times is more suitable for walls in residential applications where that large 8-inch profile might seem a little bit too large, a little bit too heavy. And for that reason, oftentimes it is a great choice for more of a residential setting, kind of that smaller profile. Again, it's available in both beveled or a straight face product option. And as you can see, typically if you're gonna have a beveled face product, it's gonna weigh about 5 pounds or so less than a straight face option. So the one thing to note on this product though, because it is 6 inches high by 18, it doesn't cover a full square foot like the Classic 8. It's 0.75 square feet or 3/4 of a square foot. So for example, if you are looking at a wall project that you needed 100 square feet of wall coverage to determine the number of units you would need, you would simply divide 100 for your square footage by 0.75, which would give you 133. So you would need 133 Classic 6 units to cover that 100 square foot of face area. Next product I want to look at is the Colonial 8. Now, personally, I really like this product and I like the look, and I'll tell you why. About a year ago, before I came to work here at Rockwood, I was working as for a construction company, a large commercial wall builder in Denver. And the company I was working for was really not only one of the largest specialty wall contractors in Denver, but one of the largest specialty wall contractors in the entire country. And I started work there in about 2010. And in that Denver market, a lot of developers really like that look of the ashlar wall type appearance. And it was very common for projects that we would bid on for the developer, the architect, or the owner to say, yeah, we definitely want that ashlar look, because they've seen it around the Denver market quite a bit. The one thing I can tell you though is that a lot of ashlar pattern walls aren't as easy to install, they're not as easy to estimate, and they're not as easy to order materials as you would find in the Colonial product. Many of the other ashlar walls require different patterns. So you'd have a 2-course pattern or a 3-course pattern, and they're kind of set and laid out that way. And the engineers actually have to lay out the wall profiles in those patterns. With the Colonial 8, you're really looking at it's 3 different wall faces, and it's on two different pallets when it's delivered to the job site. So up above, you can see we have just a straight face, straight split product. And then down below, we have a unit with a score kind of favoring the, in this case, if you're looking at it from our direction, it's kind of a score on the right-hand side of it. Well, as you may or may not know, these units are made Siamese, so face to face, and then they're split. So when this unit here, the lower unit, is split, you basically have the inverse of this. So instead of the score being aligned here on the right side, it's going to be aligned on the left side, giving you that look of, very random appearance in that ashlar look. And very easy to install, because from a contractor's perspective, you're kind of just laying, one size unit with 3 different faces, and it's just set randomly. So it's a great product option. Now, the Colonial face is also available in the 6-inch product and some of the other Rockwood products that we're going to be previewing here in just a minute. But again, you can see in the 6-inch, that lower profile for lower height walls really gives it a look of, you're not seeing the same pattern of a running bond over and over and over. It's broken up, and it looks like there's many small pieces kind of within the overall appearance. And when it's done in these blended colors, it really pops and gives it a high-end look. And it's, from a manufacturing perspective, it's not difficult to produce. From a contractor perspective, it's very easy to install. A newer product rolled out about 6 years ago called the Premier 8, and it has continued to gain popularity and use across the country every year. And if you think about it, really none of the other major licensing companies like a Rockwood has done anything new in the past 10 to 15 years. It's kind of, they're saying with this, the same old, same straight face look, same, basic unit. They might tweak a thing here or there as a product extension to make it a little bit different, extend the patent life, but nobody's done anything really innovative. And the Premier 8 really is innovative, and it's different, and provides a lot of obvious advantages to both the manufacturers and to the contractors. A lot of that has to do with the fact that you're getting 1 square foot coverage, so it's an 8 by 18 inch face, so you're covering a full square foot. But the weight of this product is what's really significant, being that it's 54 pounds. And this light weight, of course, it makes it more cost effective for producer to produce and provides maybe a better, more competitive selling price, sales point, and more profit for you as well, because you're using less material. Again, the lightweight plays into how many units can fit on a pallet and how many units can fit on a truck. So we can get over 800 square feet per truckload, which potentially allows us to ship to a little bit further, maybe a different market that we haven't been able to reach into as cost effectively. So that's certainly a great advantage. And from a contractor's perspective, it is easier to handle, it's lighter weight, it's easy to install. And that's not always the feature and benefit that an owner of a commercial wall company wants to hear. Is like, well, it's lighter, it's easier for your guys to install, they'll be less fatigued. Yeah, they get that a little bit, but ultimately that cost and how it transfers to how many square feet are getting on a truck, the sales point, and that it builds really efficiently is where a contractor sees the advantage. I mentioned in a previous slide about the Colonial face, and that the Colonial face option is available on many different Rockwood products. And again, Colonial face is a great upsell or look to this Premier 8, and it can be done in the Colonial as well. The Vintage 6, this product is certainly kind of geared more toward that backyard and residential, but I can tell you our sister company here, Rochester Concrete Products in Rochester, Minnesota, has seen the use of this product expand into commercial use for corporate campuses, malls, and even plaza settings. So it is getting some use and some specifications driven in that market space. And one of the main reasons is that it's versatility and the use. So because this product is finished on 2 sides, you can easily build a parapet wall. So the example here, you can see the obvious parapet application, but the lowest portion of this wall is actually a retaining wall. It's kind of supporting that patio. So it's a parapet wall, retaining wall. It builds columns or even kind of end pedestals, or any combination of these types of things, because it is finished on the 2 sides. And how that's achieved really is, if we look at the first unit, it is 6 inches in height, and the long side of the unit is 18 inches, and it's got a draft or a taper on just the one side. So this side is going to be more straight on the one side and have a draft or taper on the other. And then the short side of this product is going to be 16.5 inch. Again, it gives you another dimension. So we're going to have, when we're done with this, we're going to have 1, 2, 3 different pieces, and there's going to be 2 different sizes per piece. So a total of 6 different sized units that are kind of randomly set in there. For the middle unit, again, 6 inches. On the long side is going to be 12, and the short side is 10.5 inches. And for the small unit, it's 6 inches on the longest side, and then 4.5 on the short side. Contemporary wall. So this is a very clean line, smooth face look that kind of first gained popularity on the East Coast and really even north of the border up in Canada. And this look and appearance has continued to gain interest over the last 3 to 5 years. Now at Rockwood, we've seen, and we've kind of had the benefit of seeing different versions of this look. Rochester Concrete Products, a sister company here, manufactures a contemporary wall. And they've had good success, not great in its first year being launched last year. But again, we're seeing a lot more popularity and growth of this. We really feel that because of many of our producer partners are, their standard equipment is a 3-at-a-time machine. We want to have a product that first and foremost works well on a 3-at-a-time. And that's probably step one. Now, this is still in the product development phase, but we want to maximize the efficiency of the machine and also make the ease of handling. So some of the units that we've seen and that are out there with this contemporary look, they get pretty massive, they get pretty heavy, and they almost get to be a machine set. So our thought process behind this is it's still going to be a handset, lighter weight unit. For the heights, by integrating a 3-inch and a 6-inch, you can play with that height and have just a single length at an 18-inch, which helps maximize that footprint of the machine. Now, if you work for a company and you have a large board, big board machine, Tiger, something like that, certainly contact us. We're more than happy to work with, some version to best fit on your machine or your board. But as designed right now and in the product development, it's designed to be a 2-height type product with a single length. And one of the things too that we're seeing a lot is that the colors that are being used are a little bit different. Not often do you see an onyx or a black color, but in this contemporary look, the whites, grays, blacks are kind of the popular look. And I think largely due to the fact we're not splitting aggregate, and with a split face, it's got that smooth appearance to it. Compact fire pit. So I don't know how many people are familiar with this. It's been around for a while, but again, going back to Rochester Concrete Products, we've seen a lot of increase in the last 45 days or so, increase in demand for fire pits, backyard kits, and I think it's largely due to the kind of the stay-at-home lockdown orders. People want to do, small, easy, do-it-yourself type projects around the house while they're spending more time at home, maybe going on less vacations and things coming up here in this foreseeable next 2 to 3 months. And this is a nice little feature to have in the backyard. The best seller for the backyard kits that we've seen from Rockwood is really the Grand Fire Pit, which is typically a tumbled product. Now, if you're a producer that doesn't have that, a tumbler, doesn't have that flexibility, this would be a great option. And some of the advantages of the compact fire pit, you can see is this has a 42-inch outside diameter versus a 48. So this compact fire pit weighs 680 pounds versus 1,000 pounds that we would typically have in the Grand Fire Pit. It's a 3-at-a-time mold, and each cycle it makes 9 blocks. So it basically 3 cycles you could complete the manufacturing process required for this compact fire pit. It's just a little bit smaller version, not noticeably, but certainly more economical, and I think gets us into a very competitive price point. Again, it can be tumbled or non-tumbled. So again, potentially reducing the additional costs that would go into the tumbling process. So if your company's considered this, and you don't have something online, this compact fire pit might be a great thing to bring on, especially with, as we're seeing across the country, increased use for this type of product. That's all I'm going to cover on the Rockwood products. As many of you know, we have many more products and options to choose from, and certainly contact us if you have interest or you want additional information on those. We'd be happy to pass those along. Quickly, I want to go through just some features and benefits that you might have to explain to customer, contractor, homeowner, architect, an engineer, or even a developer. So the benefits of segmental retaining walls, they've been around, they're not new anymore for sure. 30 years of history, and we know that they're very high strength, low absorption concrete. They're very durable. From an aesthetic standpoint, as you've seen in just a few of the products that we've rolled out and talked about on the Rockwood side, there's a lot of different options, a lot of different color options, face textures, ashlar look and appearance. So there's it's almost limitless with the different appearances that we can do out of these segmental concrete blocks. Again, they're very easy to install. It's almost as simple as just kind of determining that layout. Where is that grade separation that you need, and what are you trying to outline or to either hold back or hold up? Get your wall layout, get a good level, set and level your base, stack it, backfill it, and repeat that process. So very, very easy in the field. And because they're modular, you can get them into areas where you can't get concrete cement trucks, or you'd have to deliver it by wheelbarrow. Very easy to get into the backyard as well. And probably the number one reason for the growth that we've seen with this product over the 30 years is they're just very cost effective. When you compare the other options that you have with cast in place or masonry with veneer, they're very cost effective. Okay, I want to get into some SRW terminology, and we're going to start with just kind of a basic gravity wall. And the first thing I want to cover on this slide is when we're talking about wall height. It seems pretty simple, pretty obvious, but it's very important to understand that the wall height of a segmental retaining wall is defined as from the top of the leveling pad to the top of the cap. So you would think though, well, okay, what if we had, manufacturer recommendations is to bury at least 6 inches of block. That's 6 inches of block, it can't tip over. So why is that considered part of the overall design height? Or conversely, we might even have as much as a foot or 2 feet of block buried. So our exposed height might be 8, but we could have 2 feet buried below. Our design height and what we would have to look at for engineering that wall would be the 8 feet that's exposed plus the 2 feet below. And again, I want to point out, we use a leveling pad, not a footing. That's going to be important in a slide that's coming up. Some of the other things I want to point out in this slide is, number one, the unit drain fill. So drain rock is very important from the fact that it allows the water to escape from behind the wall. And this drain rock is also placed in between the units, in the cores of say a Premier 8 unit, which helps add additional weight and shear capacity and additional stability. This 1 foot zone helps with drainage, but it also helps assist in our compaction efforts. So when we're placing soil behind this drain zone of rock, it's not placing too much force when we're doing the compaction efforts behind it. The other thing I want to point out on this is drain pipe. So so many times you see a cross section just like this one, and it shows a drain collection pipe. And I've heard over 30 years people say, you should always use drain pipe. It's good, cheap insurance. And there is some truth to that. However, if drain tile or drain pipe is used, behind the wall like this, it's important that there's a drainage plan or a place to take it. Because if you have a free draining zone of rock like this behind the wall and a drain pipe down here, if water gets into this area, it will find that drain pipe. But as you notice in this cross section, the drain pipe, and in many cross sections like this, is shown below the finished grade out in front of the wall. So where's the water going to go? And in this case, it would have to be daylighted someplace out the end of the wall, either end of the wall. Typically, it's going to be the low side. Makes sense. The other option that can be used too is, in order to get this drain pipe up, a lot of times the leveling pad material, which typically has more fines in it than the open graded rock here, you could bring that material up to the elevation of finished grade and cut blocks and daylight it right out the face. So I just wanted to point that out. Drainage collection pipes are a great idea, but there should be a plan and some place to take that water. Here's an example of a reinforced wall. So in the gravity wall, we're really relying on the height of the blocks and the width of the blocks and the weight of this entire column of blocks to resist and retain the earth pressures behind it. Well, at some point, we get too tall and our column of block is too narrow and really not heavy enough anymore to retain the soil behind it. That's where we have to introduce geogrid soil reinforcement. So by adding layers of geogrid in compacted soils, so we still have our drain rock. This area here of compacted soil is called the reinforced soil zone, and it's brought up in 8-inch lifts, compacted and brought up to where we would need or be required to have another layer of geogrid. It's placed over to the compacted soil, and we repeat that process. Now, instead of just relying on this column of narrow blocks, we've created a big mass with our reinforced zone that is going to hold back. You can see over here is called the retained soil zone. So it is, in essence, it's a gravity system, and we're using soil to help create additional weight. Reinforced soil with geogrid to create a large block that's going to retain our retained soil zone. The other thing I didn't point out is setback or batter. We talked about it when we were looking at the Rockwood products. Setback or batters are referred to the amount that each course is going to set back. So if you have a 1-inch setback per course on an 8-inch high block, it's about 8 degrees. And that's important in overall design stability, construction stability. And I'm going to talk about this in an upcoming slide in terms of just how much that does help when we're looking at reducing the earth pressures behind the wall. Now, if you were to take that cross section, those last two cross sections we just looked at, and see it in a real life application, this is what it should look like when you're completed. You see in this case, it was more of an open graded base material. You have your column of rock behind and in between the units, compacted soil with geogrid laid flat and tight without any wrinkles in it. And it's just kind of a visual of what that looks like, what it should look like behind the wall that you see as you're driving down the road. This is a neat little experiment and diagram that just illustrates more how geogrid works. And what's done here is up in the left-hand corner, we've taken soil. In this case, it's kind of a granular rock material. And taken that material and put it in a hinged box. And we take that hinged box and we apply a load to it. And when we apply to a load to it, you can see how it kind of squishes out to its angle of repose. And not friction angle, but really more that load at which it wants to kind of settle out. Excuse me, at. Now, we repeat that process, only this time we're going to kind of tamp down the soil, add layers of geogrid, tamp down more soil, add another layer of geogrid, tamp down the soil. And you can see when we apply the same load on that hinge box, how vertical it holds and confines all those soil particles with the geogrid. So when we were looking at the reinforced wall section, our retaining wall face would be out here, and this big mass of reinforced soil is kind of our new coherent gravity system that's retaining our soil. There's really two different types of retaining walls and how they're being utilized on a site. You either have a fill wall or a cut wall. And the function is we're either trying to make room for a building or a road, or we're trying to support a building or a road. So if you're looking here, you can see an existing ground line that came through the site. And in this case, on the upper wall, we're trying to create room or space and cut back into this existing grade or this existing ground line. And we do that, that's referred to as a cut wall. If it's on a downhill side and we're trying to level off a site, we refer to that as a fill wall. One thing I want to point out, and it doesn't matter if you're on a residential backyard site or if you're looking at a set of commercial plans, a lot of times developers, engineers, or architects, they're looking at the site and they're like, oh, well, we got to fit our building in. We have to fit our road in over here. But man, we've got this big grade separation. We're going to need a retaining wall. But the retaining wall is kind of the last thought. And many times that retaining wall gets very close to the property line. So it's important for when you're looking at a set of plans, where is that property line and how much room do I need to cut out to make room for maybe my geogrid soil reinforcement and lay that back at a safe safety cut. So that's an important thing to make note of when we're looking at what's going on around our walls. Other things that we need to look at is, we call them design or site considerations. Looking at a retaining wall, it might be a set of plans. Again, it might be in a residential application or in a backyard. First thing is wall layout. Where's the wall going and what's going on behind it? Do we know of utilities? Are there property lines? You know, make sure you get your 811 call in to get your utility locates. If it's a commercial application, typically you're going to have to look at not just the grading plan to see how tall the wall is, but it's a good idea to look at utility plan, site plan, see if there's anything behind it. Surcharge and traffic loads. Again, traffic loads I think are obvious. If someone looks and says, well, there's going to be a parking lot right behind my retaining wall, that becomes really obvious that, hey, there's a surcharge that we need to take into consideration when we're engineering our wall. Or maybe it's less obvious. It's along the side of a garage where the homeowner wants to park their RV. Well, that RV being backed in and parked along the side of a garage, if the retaining wall is 3 or 4 feet away, that would certainly be a surcharge load. The one I highlighted here, though, is back slope. So a lot of times we don't really consider, if we're going to build a wall that's 4 feet tall, but the slope continues up another 4 feet, we don't always think of that obviously as being a surcharge load, but it is. It could almost be considered, if we had a 4-foot wall with a 4-foot slope on top of it, we might have to look at, from a design or engineering perspective, that being an 8-foot tall wall. That's how much additional load is being placed on it. Another thing that's important from an engineering or design consideration standpoint is what type of soils are on site. And rather than get way deep into it, I can just sum it up, is that sand sandier materials, granular, more free draining soils are good, and clay soils that have high silt content that are more prone to water absorption or changing its property when moisture is added are bad. So granular is good, silty clays typically are not as good. And a lot of that is due to their properties and how they react to water. Retaining walls are built outside, they're going to get introduced to water. Foundation and bearing capacity. On a commercial site, that's typically handled by your geotechnical engineer. They're going to be able to look at and test the stability of that soil. If it's in a residential type setting or application, you want to make sure that it's non-organic, so you're not looking at black dirt, you're not looking at a lot of roots and things like that. And if you're walking in it, your boots aren't sticking in it. So those are kind of the barometers that you would look at. Water conditions, sometimes they're obvious, sometimes they're not. In a residential type application, the things that are going to, potentially introduce or add water are going to be gutters, downspouts, things that would potentially be directed at the retaining wall. You're going to want to address those, water capture areas and get it out around the wall by extending it with, solid drain pipe or something like that, but keeping water away from the walls. Yes, we do have drain rock behind the wall, but retaining walls are not designed to be a drainage system for the site. And it's interesting, I just had this conversation with the developer Monday of this week. They were talking about, well, yeah, but you have all this rock. So what's wrong with the water from the parking lot being drained toward the wall? Well, the drain rock that's there is intended to assist and reduce the amount of water buildup behind the wall and poor soils being contained, but we're not trying to divert water to retaining walls. That's never a good idea. Other things we need to look at is it a tiered wall application? So is it a single height, or do we have multiple tiers, and how close or how far apart are they? I'm going to talk about that in a minute. Or walls that are built on a slope. And I got some slides to look at that and further explain that as well. It's funner to look at pictures anyways. So drainage considerations. We've talked about number one already. That's kind of our drain zone, 1 foot behind the wall, as well as drain rock that's placed in between and within the units. That's our kind of our first line of defense. Number two is potentially capturing surface runoff. So if we do have a slope, maybe it's the example of the one I just described about a developer saying, well, what's wrong with the water coming down toward the wall? We don't want that. If that's going to be the case because there's no other place to take it, it might not be a bad idea to put in a concrete flume, or even it could be geosynthetic filter fabric with riprap or something over there to help carry and transfer and not allow that water to get down into our reinforced soil zone. Third line of defense here, this is typically more site specific. If we're in, I explained it a couple slides ago, we either have a fill wall or a cut wall. It's not very common that you would see this drainage composite, or we call it strip drain, in a fill wall application. However, in some cut wall applications, there may be water that could seep from the embankment. An old hydrostatic head that when the excavation occurred, now we're starting to see water seeping out of that embankment. If we see that, we want to stop what we're doing, let either the engineer of record, if it on a commercial job, to make notice of it. But it's really pretty simple. It's just a kind of a board with a plastic material in here, geosynthetic geotextile on the outside of it. And it captures this water, brings it down to a drain and taken out. And then number four is the drain tile. We talked about that in the cross section of the gravity wall and reinforced wall slide. Again, it's important to have a plan. So these drains will catch water, but we have to make sure we get them out from behind the wall, or they will saturate and saturate the foundation. So what I want to talk about on this slide is the first photo up here on the left-hand side is reinforced wall, and we're typically the length of the geogrid is going to be, in most cases, about 70% of the design height of the wall. So if we have a 10-foot high retaining wall, these geogrid lengths are going to be about 7 feet in length. If we had let's say a 5-foot wall, we want at least 4 feet of geogrid. So I'm going to say it's 70% of the design height is a rule of thumb with a minimum of 4 feet. And the reason I say that is, the block, say a classic 8 unit, is 12 inches deep. The geogrid is going to fit into that block a foot. That really only gives us about 3 feet from behind the wall that we're reinforcing. So just a rule of thumb on those design lengths. Now, if we move down to the illustration on the bottom, here we're going to apply a traffic load. So a live load of 250 pounds per foot. That doesn't necessarily mean that our geogrid reinforcement lengths are going to get longer. If they were 70% in our upper diagram on the left, they'll still probably be 70%, given all of the other conditions being the same, and just introducing the load. But the additional load might require an additional layer of grid, and it might require our layers of geogrid to be spaced closer together. So that's really the difference on how it works. The things that typically drive the length of geogrid are other external forces, like a long slope, back slope behind the wall would make our geogrids longer, or a very steep toe slope could make our geogrid lengths longer. Those are typically the external forces that are going to lengthen our grid beyond that rule of thumb of 70% of the wall height. I'm not going to spend a lot of time on this slide, but these would be alternative reinforcement options if geogrid can't be used. And in this case, we would have potentially a soil anchor, because we're going to get too close to a property line that might conflict with the excavation footprint for the geogrid. So an anchor would be put in, and we'd have hardware that would connect a couple of courses of block together. So that's an example of an earth anchor. In a rock anchor, maybe we can't make the excavation work because there's rock back there, and we can't get to that 70% design height. So in those cases, we would drill into rock and use a capsule. It's like an adhesive that would anchor that bar into the rock. And again, you'd have hardware that would come out and kind of reinforce and attach itself to the wall. Or the last section is kind of a steel pile anchor section, so an H pile. This would be where you have a really tight property line constraint, or maybe there's a large utility back here that can't be disturbed. And this would work, I'm going to say up to about 15 feet or so. Typically, this steel pile section is going to be about twice the height of the wall. So if this is a 10-foot high wall, this steel pile is going to be a length of 20 feet. That gets to be a big piece of steel to pick up and set into a caisson. So those would be alternative reinforcement options. That project that you come across, hey, there's not room for geogrid, give us a call, contact your sales manager or someone here at MSE, and we can find an alternative method for that reinforcement. Permitting and requirements for retaining walls. You're going to find that these vary quite a bit from state to state, county to county, city to city. And the reason that they do vary is that people that work in these offices, they're typically not considered experts at retaining walls. Yes, they have to go through and review the plans and the submittals and approve retaining walls and determine, okay, how much does it cost and what is the use tax and things like that. But they're not really design or engineering experts. So the International Building Code has given them guidelines to kind of help protect and steer them so they can use their best judgment. And I will tell you that what the 2015 International Building Code says is that any wall that's under 4 feet in height, measured from the bottom of the footing, again, in our case, it's a leveling pad, so it's the top of the leveling pad, to the top of the wall, unless it's going to support a design load, is exempt from a permit. Now, unfortunately, somewhere down the line, this has been taken way out of context, and it's become the rule of thumb by, unfortunately, city and county people, or even homeowners or contractors. So people that know little about walls to people that should know a fair amount about walls, is that any wall that's under 4 feet, you're safe. You don't need a permit. And then they've taken that a step further to say, well, if you don't need a permit, then you don't need engineering and you don't need geogrid. Those are all 3 separate different issues. But I want to break this down a little bit. So I've mentioned that the minimum embedment depth that we would suggest for a retaining wall from Rockwood is 6 inches. So therefore, the maximum exposed wall height under the guidelines shown up here by the 2015 International Building Code is that the maximum wall height you could end up with is about a 3.5 foot exposed, because we're going to bury 6 inches of block. And that's assuming, again, that it's not going to support a parking lot or surcharge or have a back slope, and that there's no toe slope. So that's just kind of a little clarification. What you do with that information and how it's used out in the marketplace, I've been fighting it for years, but this is what it says, and this is what it means. Tiered walls. So our recommendations from Rockwood are, if you look at the overall, again, design height from the top of the leveling pad to the top of the cap, you should maintain 2 feet, 2 times that height. So if this was going to be a 5 foot wall, we want to be back at least 10 feet for this upper wall not to be loading or supplying a surcharge to the lower wall. If we look over here at the other figure, say we had a 6 foot retaining wall and we just don't have room. We can't get 12 feet back and fit it in our profile. That's fine. You can certainly do a tiered wall in that setting. And if we're going to have a 12 foot wall, we're probably going to have 8 foot geogrids at the bottom. So we'd have 8 foot grids down here. And then the upper wall would probably have, probably we'll call it 4 to 5 foot geogrids. It'd be a kind of along that same plane is where those geogrids would go to. So it's certainly okay to have walls, tiered walls closer than twice the height. It's just that they will impact. This upper wall in this diagram is putting additional load and surcharge on the wall below it. That's what Rockwood says in terms of the design recommendations for tiered walls. Now, National Concrete Masonry Association, which is kind of our industry association that helps provide us with additional guidelines, takes it even a step further. So in this case, they say if the total combined height of the tiered walls is less than 6 feet and the distance of the walls is greater or equal to 2 times the height of the lower wall, that it can be structured per manufacturer's recommendations. But they also say if the horizontal spacing is, if you're less than twice the height and the overall combined height is greater than 6 feet, get it reviewed by a professional engineer. So basically they're saying if you had a 4 foot wall and a 4 foot wall and you had 8 feet of distance in between them, you should still have an engineer at least look at it for you. And I want to, again, extend the services that we have here at MSE, right here in the Rockwood office, to, if you come across this situation, you've got a overall design height of 8 feet or 10 feet, 2 4 foot walls or 2 5 foot walls, give Jeff Seberg a call, have him take a look at it. He's going to probably ask you a few questions about what's going on around the site, but he could certainly give you some design design recommendations that you could pass along to the contractor or the homeowner. Okay, gravity walls. Again, we talked earlier about 4 feet being that magic number that you don't need permits, grid, or engineering. I want to give you an example here of a wall. Let's go to a wall with 1 inch setback. So we're going to use classic 8, and we're in great soils. Well, as you can see here, the highest we can really do as a gravity wall with great soils and a flat level back slope and a flat toe is 3.67 feet. Again, that is from the top of leveling pad. Would a 4-foot wall fit in this? Yeah, probably. But when you look at the factors of safety, 3.67 is about the maximum height that you want to go. Now, if we came down to some clay type soils and we're going to have a slope up behind it, and in this case, let's use a 3-to-1 slope in clay soils. The maximum gravity wall height that you might be able to get out of the block is less than 2.5 feet in height. Again, that's from the top of leveling pad. So soils, surcharges play a big role into what can work or not work before we have to add geogrid. And I know a lot of people are like, oh, I gotta add geogrid, that's a big deal. It's really not. Geogrid does not cost a lot of money anymore. It does require a little bit larger excavation footprint, but we're only talking in walls of this height, and 3 feet of additional excavation behind the wall for it to work. Getting into the installation process, so I've mentioned this a couple of times already. We want to have a minimum of 6 inches of block buried, and our trench depth, the leveling pad thickness, is 6 inches. So in pretty much any case, from where the finish grade is out in front of the wall to the bottom of our trench is going to be about 12 inches. This material that we're putting in the trench, we want it compacted to 95% standard Proctor. That's what we recommend here at Rockwood. So if you're in a residential setting, how do you know that? Well, you don't, unless someone actually comes out and tests it. But what we recommend is use a granular soil, so it can be open graded or kind of a road-based material, and use the right piece of compaction equipment for that type of material. So you want to use like a vibratory plate compactor to vibrate and compact and get that material settled down. Above that, it's okay to put a 1 inch layer of sand or lighter uncompacted material to help assist in leveling. The width of the trench, you want at least 6 inches on either side of the unit. So if we have a 12-inch deep unit, we want 60 inches of room on either side of it, which you're going to want anyways, just for alignment purposes. So the width of it's going to be about 24 inches. Block embedment depth on a slope. So you mentioned numerous times that, hey, our minimum block and embedment depth is going to be 6 inches. Well, block embedment depth is also a function of the wall height. Rule of thumb is 10%. So if you have a 10-foot high wall, you're going to want about 1 foot of block buried. Now, and that's going to be in a level setting. As we get into a sloping toe type condition, we're going to increase that. So if it's a 3-to-1 slope, you're going to have 1 foot of block and buried on a 10-foot wall, plus an additional 1.33 feet. So you'd have 2.33 feet buried for a 10-foot wall on a 3-to-1 slope. And give an example in a residential type setting. So I've been on many calls where you're out and doing a measure up for a homeowner, and they might have 6 feet of grade separation that they want to build up a wall so they can have a nice level patio. And you give them the measurements, they understand that this wall is being priced on a price per square foot basis, and you give them the number and they have that sticker shock, and you feel for them, and it's like, I know, but that's kind of what we have to do. And the homeowner would suggest, well, what if we just made the wall shorter? Like, what if we didn't start down here at the bottom of the hill What if we went halfway up the hill? Well, unfortunately, that doesn't help solve their problem, because if they had a 6-foot wall and they want to go up and make it only a 4-foot wall, you're going to have to add additional block below grade. It's going to come out to about that 6-foot mark anyways. So you kind of end up chasing your tail a little bit, trying to reduce that square footage area by chasing it up the slope. Toe slopes are going to require greater block and depth, embedment depth, and I'll give you an example coming up in one of our failure slides too. So here's an example of using string lines and compaction equipment to level and compact the base as we're setting the units. The slide on the left, give you an example of something that I don't think is the best tool for what they're using. They're using a great road base type material, but the compaction equipment they're using in this case is a jumping jack. It's not that it doesn't work, but it's more of a dynamic type compaction where a vibratory plate would be actually easier, faster, and more efficient than this jumping jack that they're using in this case. Here you can see that as they're adding gravel and filling up that trench, they're trying to get relatively close before they start fine-tuning it by getting the elevation fairly close. And then here they're adding the fine-tuning with rake and other tools. Here's an example of a vibratory plate. You can see the first pass that I made here, how it just densifies it. Is that 95% standard compaction? I don't know, but it's good quality material and it's been compacted with the proper piece of compaction equipment. A couple, 2-3 passes over that type of material with a vibratory plate should be sufficient. Setting and aligning the base course. So in the illustration and the example that we have here, they're running a string line and they're kind of doing it off the front face. I don't like running the string line off the front face because the front face, whether it's a beveled face product like shown in this picture or a straight face product, is designed to be random and not perfect. Where along the back of the tail of this unit, it's a machined, consistent edge. So in this case, I personally prefer putting the string line off, running it off the back of the units. So you want to level the units from side to side and check them from front to back. Some contractors will put in additional batter or taper, making the tail slightly lower than the face. That's not wrong. However, if a contractor is going to add additional batter or tilt in the base of the block, it's important that they maintain consistency. So if this unit is dropping 3/16 of an inch, that the unit next to it and all of the units next to it maintain a 3/16 of an inch setback or batter. Because what would happen is if you're at 3/16 of an inch batter on this block, and then the next one's at a 1/2 inch, and then the next one's at an 1/8 inch, the units the tails aren't level, and when you place the additional course of block and slide it forward, it's not going to engage in the same spot, and that will affect the wall alignment as you look down the wall. So it's important that if you are going to drop the tails or make those adjustments, that is done consistently. Here you can see the contractor's doing a very nice job of string lining and keeping units level side to side in the front and in the back. Mentioned the drain tile. So this is an example of a drain tile with a sock. The drain tile itself is perforated to allow water to come in and carry down the channel. In this case, they're daylighting it or cutting it out of the face of the block. The unit drain fill, we talked about that. It goes within the units and 1 foot behind the units. It should be a clean, so less than 5% passing the 200 rock, and again, placed within and behind it. Here's an example of it being placed. So you can see the drain rock area about 1 foot, and then the backfill material. In this case, the contractor is using kind of an import backfill material. You can see the on-site cut right here is more of a clay or a silty material. This is certainly not the same material that they've excavated out. This is coming from a quarry or a pit. And we like to see this material placed and compacted in 8-inch lifts. In this case, the lift is a little bit thick, but as you'll see in the upcoming slides, the contractor does a good job of kind of leveling and keeping that material leveled out and compacted. If the lift size gets too thick, a couple problems with it is, one, it won't compact all the way through, and the other thing is it will apply additional or undue force on the retaining wall. So we want to keep those lift sizes down to 8 to 12 inches. On this particular site, the delivery method for the backfill was front end loader, kind of over the face of the wall. And they have a bobcat behind the wall, leveling that out as they're going. Here's another photo of that. So front end loader dumps it over, the bobcat keeping that material level. And that's important too. This is a fairly heavy piece of equipment. He's relatively close to the back of the wall, but it's important that this material is kept level and in small lifts, and you should be able to drive a piece of equipment this size. This is a track machine, so it's putting a little bit less force on the wall. But the key to not pushing this out and getting good compaction is smaller lift sizes and keeping that material level. So not all the weight of the machine is going toward the wall. In those areas, though, that are tight up against the wall, you can kind of see it in this slide, the sheep's foot imprints. So they were using a large, heavy sheep foot compactor roller behind this wall, which is going to be just too large and to put directly behind the wall. So directly behind the wall, they're using a lighter weight handheld material or handheld compaction equipment for that distance of 3 feet directly behind the wall. After your compaction efforts are done and your unit drain fill is placed within the wall, we want to make sure that we sweep the units clean and get it ready for geogrid and stacking additional courses of block. Any little rocks, pebbles, things like that that are left in there when the next course of block goes on can create kind of high points and create stress loading on the block. So we want to make sure that everything is swept off nice and clean. And here you can see for the soil reinforcement, it should be the type as shown on the retaining wall plans, the length as shown on the plans, and at the correct elevation. We want to lay them flat and free of wrinkles so that when we add the next course of block, everything is laid tight. The Rockwood alignment bar is brought up and engaging the grid and the blocks below. So in this wall application, it looks like they have 2 course spacing between layers of geogrid. So they're going to get a stack of 2 courses of block. Again, we want to keep the lift size down in this case to that 8 to 12 inch range, but it's okay to go ahead and stack up the 2 courses and bring them across. And that completes the kind of the sequence of the process of basically leveling the units, bringing the wall, erecting the wall face, placing compacted material, all the way up to our top of wall elevation. Now I've got just a couple slides left and want to kind of illustrate or hit home why these best construction practices are important. So in the previous slides, we were talking about the importance of keeping your lift size down to 8 to 12 inches, using good backfill material. In this case, you can see this is what a fat clay looks like, big chunks of soil. And it's obvious that the contractor was not placing and compacting this clay material in 8 to 12 inch lifts. So we have all this heavy weight of soil. Also, you can see there's no drain rock that was incorporated or placed within the units as it's being built up. So this is a bad application all around. We have fat clays right against the back of the block, material that was never placed or compacted correctly or properly, and you can just about guess what's going to happen when water or a rainstorm comes in. All of this is just going to just flow right out the face of the wall. This is actually a very dangerous application in a fairly tall wall. So it's a wall that hasn't failed yet, but it doesn't have much of a chance of being successful. Here's an example of two things. One is site drainage while the wall is being constructed, as well as geogrid coverage. So geogrid needs to be placed in continuous. There's a roll direction. So in the direction that you would roll it off the roll, that is the strength direction, and should be placed perpendicular into the wall. And it should be continuous. There shouldn't be large gaps from where you lay a strip of grid to where the next strip of grid is placed. In this case, you can see the contractor put some geogrid in and then skip the space and then put another piece of geogrid in, then skip the place, put another layer of geogrid in. This needs to be continuous. So this should be a continuous layer of grid. The geogrid is actually coming out of the face and just is laying flat. The other issue that they have going on here is that you see all the standing water down in front of the wall. Well, as the wall's being constructed, once you get up 2 or 3 courses, and it's very common, you have the excavated trench out in front of the wall. We want to make sure that we're filling that area out in front so that if you do have a rain event during the construction process, that the water can be diverted and it's not going to pond up and pool in front of the wall. Also, in this case, we have a massive amount of material that maybe the general contractor or the earthwork contractor hasn't addressed yet. They're probably going to move this off the site to someplace else. This is not a great area to store additional material because it creates a large capture area and helps divert a lot of water directly toward the wall. So I mentioned in the last slide that there is a strength direction of the geogrid. The strength of the direction is, the directional strength of the grid is as it's rolled out and it's cut to the correct length, it's placed in perpendicular. This is an example where the contractor rolled the grid out the length of the wall and placed it. So this has really no effective strength property for retaining the wall. We also looked at illustrations showing it should be placed on compacted soil and laid flat. This is an example of a poor installation with the use of geogrid. I mentioned walls built on slopes and failures. So what happens in a slope situation like this, we have a fairly steep toe slope, probably a 2-to-1 or a 3-to-1 toe slope out in front. And when we put the weight of the block and the weight of the soil, as we do in a reinforced retaining wall application, all of this additional weight that's created not just from the block, but from the additional soil behind it, has pushed down and created this toe slope out in front to fail. So again, walls built on slope, typically we're going to have deeper embedment, and this is just an example of a global stability type failure. Another type of global stability failure is the materials being wet, and in this case, this job was in Denver, Colorado. It was a unique soil type called a soapstone, and just like it sounds, a soapstone, it was rather a slippery surface. So as the retaining walls were built, and we've added the block, and we've added the soil, and another tier of block, and another area of soil behind that, this additional weight down in this slippery soapstone caused the base of this wall to just shear off. And this was on a concrete footing, and it sheared out and caused the upper wall to collapse and the lower wall to slide out. So I did have the one slide that showed what are some options. If there's not room for the proper or the correct geogrid length, what can we do? Well, we can add, as I said, rock anchors or earth anchors or potentially H-piles. In this case, there wasn't room and there were no rock anchors used. So we have a retaining wall that's almost 20 feet in height and a geogrid length of about 5 or 6 feet. That certainly doesn't fit the rule of thumb that we talked about, that our geogrid lengths are going to be 70% of the design height. This is a 20-foot tall retaining wall. It should have geogrid lengths of probably 14 feet long. So the 5 feet isn't going to cut it. Even though there's rock, kind of a rock ledge back here, the added weight from all the stone placed directly behind the wall and this rock ledge was too much and caused the wall to collapse. And lastly, so this is the last slide, any type of walls can fail. They can be cast in place walls, they can be segmental retaining walls, or even natural stone walls. In this case, this is a natural stone wall. It was constructed probably a little bit too tall without some type of soil reinforcement going on behind it. And also, two other conditions that might be a little less obvious is there's really no drain stone. There's no drainage aggregate directly behind the wall. So as the natural material that we're looking at here goes through freeze-thaw cycles, so moisture gets added to the soil and it goes through a freeze cycle, it just keeps moving and placing additional pressure on this wall over time until eventually it just collapses and rolls over. The other thing, again, that's a little bit less obvious is there's kind of a slight hillside here which would help divert and channel water down to the wall. So it's really a combination of poor drainage, no stone, and water being directed directly at the wall. So those are our reasons for best practices. If you have additional questions on any of the things we covered today, or maybe some things that you were hoping that we would cover that we didn't, please feel free to give me a call, send me an email, or to contact any of the regional managers here at Rockwood. I'd be happy to help you out. Thanks for attending, and good luck with your next promotional or your next seminar that you're going to do. Thank you.
Thank you.